Welcome to Lesson 20, the second of our 2 lessons on geometry. In Lesson 20, we'll learn about perimeter. We'll learn about triangles and circles, and we'll take a look at 3-dimensional figures. So first, let's talk about perimeter. What is it? Why do we need to know it? And how do we measure it? The word perimeter can be broken up into 2 parts, peri and meter. Meter means to measure. What does peri mean? Well, a periscope allows us to see around things. Okay? So, measurement around. The perimeter is the distance around the outside of a 2-dimensional shape. As you can see, we have this shape that has various measurements on its side. And we add up those sides, 12 plus 3 plus 4 plus 5 plus 7 plus 8 plus 6, and we get 45. What kind of measurement will perimeter be? Will it be square units? Absolutely not. Square units is for area, and we only get that by multiplying distance measurements. Here we're adding distance measurements, and remember, way back in Lesson 1, when we add, we're counting, and the place value must be the same. So all these must be in the same measurement. So if those numbers were all in feet, the answer would be 45 feet. If those numbers were all in centimeters, it would be 45 centimeters. Why do we measure perimeter? Why? How can we use it? Well, let's assume you owned a house that was built on a piece of property and you wanted to put a fence around on the outside, the border of your property. Maybe you wanted to keep your children or your dogs in or keep other people out, whatever reason, or just because it looks nice to have a fence. How much fence would you need to buy? You'd need to know the distance around the border of your property. You'd add up all those parts, the distances of the various sides of your property, and get the perimeter, and that is how much fence you will buy. If you were putting a border around part of your garden, one of those little fancy borders that people who garden use, you'd have to know what the perimeter of your garden was. If you wanted to put up some molding at the base of your walls on your floor, how much molding? You have to know the perimeter, the distance around your floor. Obviously, there are certain very basic shapes that we need to be able to find the perimeter of. For example, the square. Now, since a square has 4 equal sides, to add up the 4 sides is kind of silly, much easier to multiply by 4. Why? Because multiplication is repeated addition. So if the square had a side of 6, 6 plus 6 plus 6 plus 6 is just as easily obtained by multiplying 4 times 6, 24. And remember, the measurement of perimeter is distance. So it's in inches or miles or meters or kilometers, not in square units. Okay? Let's take a look at this rectangle. Now the rectangle has a length and a width. If we add the length and the width, what do we get? We get something called the semi-perimeter. What does that mean? Semi means half, so it's halfway around. Well, let's see. If we're halfway around, how would we find all the way around? I want you to stop and write down the formula that you would use to find the perimeter of a rectangle if the length plus the width is the semi-perimeter. Do that now. Well, obviously, in order to find the full perimeter, we would double the semi-perimeter. 2 times the length plus the width equals the perimeter. Now, if you peeked and you saw that on the visual, that's okay. I wanted to be sure that you understood in your mind why that formula is what it is. It's easy to remember formulas. It's much more important to understand where they come from. In this particular case, length plus width is halfway around. The perimeter is all the way around, so we double the semi-perimeter, double the length plus the width. Okay, now it's time to talk about triangles. What is a triangle? Well, first of all, it probably should be called a trigon, a 3-sided figure. But somewhere along the line, someone said triangle sounds nicer. I always believed there were Madison Avenue marketing types all the way through the history of mathematics coming up with names that would sound good. And it's very interesting. There are many names in mathematics that have a ring to them. So triangle may be one of those. Some ancient Greek or Roman marketing type wanted to find out what would really sell. We want to sell these shapes. We've got to sell lots of shapes, make lots of shekels, or whatever they were making in those days. And we would come up with a name. Well, trigon, they tried it. They tried trigon. It didn't work. Triangle, sold. So he got a good commission. Everyone was happy. And to this day, we talk about triangles. Now, we can classify triangles, these three-sided shapes, by their angles, for example. Here are three triangles that can be classified by the largest of the three angles in the triangle. On the left, we have an acute triangle. That would mean that all three angles are acute. The largest angle, therefore, would be acute. The second triangle is called a right triangle. The right triangle has the largest angle that is 90 degrees. Now, you may say, how come the other two angles have to be smaller? Well, the answer is it was discovered many, many years ago, probably by the Babylonians, that the total of the three angles of any triangle, underline any triangle, is 180 degrees. Therefore, if one of the angles is 90 degrees, the other two angles must sum to 90 degrees, and therefore must each be less than 90, and therefore must be acute. So in the second triangle, the largest angle is a right angle, and that is called a right triangle. A rather important triangle, by the way, used for generations to measure things. The third triangle, the one on the right, is called obtuse, because its largest angle is greater than 90 degrees, but of course less than 180. The other two angles obviously must be acute because their sum must be less than 90. So we have acute, right, and obtuse. Those are the three types of triangles that are classified by the angle, the largest angle in the triangle. We can also classify triangles by the relative size of their sides. That was a word, the relative size of their sides. Here are three examples. The equilateral triangle, equal sides, lateral meaning side. The equilateral or equiangular triangle. All three sides are the same. It turns out all three angles are the same. Now what I'd like you to do is stop for a minute and use two facts that we just said. One is that the angles of a triangle add up to 180 degrees. And the equilateral triangle, all three angles are the same. I'd like you to stop and find out what each of those three angles measures. Do that now, please. Well, 180 divided by 3, the three equal angles, is 60 degrees. So each of the angles in the equilateral triangle are 60 degrees. Therefore, if we were looking at the equilateral triangle and trying to give it a name in addition to equilateral based on the angle measure, we'd say it was an acute equilateral triangle. Could there be a right equilateral triangle? Obviously not. The only equilateral triangle is one where all three angles are 60 degrees, all three sides are the same. If a triangle has two sides, they're the same. It's called isosceles. Two sides are the same, one side is different. By the way, we can have an acute isosceles triangle. We can have a right isosceles triangle. We can even have an obtuse isosceles triangle. Simply means that two of the sides are the same. It has been found out that if two of the sides are the same, the angles opposite those sides are also the same. So another little thinking question for you is, given what you know about a right triangle, an isosceles right triangle would have what angles other than the right angle in it? Stop the tape, think about it, and come back when you have an answer. Since the sum of the angles in a triangle is 180 degrees, and a right triangle has a largest angle of 90 degrees, the other two angles must add up to 90 degrees. If those two angles are equal, then each must be 45. So a very special right triangle is the 45 degree, 90 degree right triangle. If we have a situation where none of the angles are equal, all three angles are different and all three sides are different, then we have what's called a scalene triangle. And the triangle on the right is scalene. It has three different sides and three different angles. We can have an acute scalene triangle, we can have a right scalene triangle, and we can have an obtuse scalene triangle. So the only type of triangle in which we're restricted is the equilateral. Equilateral, all three angles are 60 degrees. It must be an acute triangle. We talked in lesson 19 about the area of a square and a rectangle and a parallelogram. And I mentioned to you that we would use the notion of the area of the parallelogram in this lesson. And of course we will right now, because we want to find out what the area of a triangle is. Okay. Notice on your screen you see a parallelogram that really has been sort of split in half along what's called the diagonal. And it has a base and it has a height like any parallelogram, but you'll notice that the two pieces in which it's been split are both triangles. In fact, if you take any triangle and get a twin of that triangle and flip it over, it will form a parallelogram. In fact, if the triangle is a right triangle, the parallelogram it forms will be a rectangle. And in fact, if the right triangle is an isosceles right triangle, when you flip it over, it will form a square. But whether it's a square or a rectangle, it will be a parallelogram. So therefore, every triangle is exactly half of a parallelogram, whose base and height are the same as the triangle's base and height. Therefore, as you can see on your screen, if the area of a parallelogram is base times height, the area of a triangle is 1/2 times the base times the height. And that is simply how you find the area of a triangle. Remember, when we find the area, the units of measurement will be square. Square inches, square meters, square miles, square kilometers, whatever it might be. How would we find the perimeter of a triangle? Is there a formula for that? Well, not really, because we have a three-sided figure, and all we do is add up the three sides. Now, obviously, when we get an equilateral triangle, since all three sides are the same, you take one of the sides and multiply it by 3. But it's kind of silly to worry about that. Most triangles tend to be scalene, 3 different sides. So to find the perimeter, all you do is add up the 3 sides. Now, what I'd like you to do now is consider the word circle. Geometric form. You know what a circle looks like. What I'd like you to do is stop the tape and write down in words what a circle is. Do that now, please. I always have a good deal of fun with my students, whether they're high school students or elementary school students, when I ask them this question, because they generally say something goes round and round. And what I do is I draw something that's like what's called a helix, going round and round. That's not a circle. And really, although we know what a circle is, we can't say it. The beautiful thing about geometry is that in geometry we can say it. What a circle is, it's simply all the points that are equal distance from a center. And those points really form a circle. Every point on the circle, and it is called a closed curve, is an equal distance from the center of that circle. And here on your screen you see a picture of a circle and its various parts. Again, the circle has a number of different parts. It's very important for us to use the correct terminology. The distance from the center of the circle to the outside, the circle itself, is called the radius. And it is marked with an R for radius. From that word, we get radiate and radial tire. All these things, something radiates, it goes out. So a radius is the distance from the center out to the circle. The D points to the diameter. The diameter is the distance across the circle through its center. You can see that the diameter is 2 radii. Again, radius is a Latin word, and the plural, I am told, for a word that ends in US, ends in II. So basically, radii. But if you want to call them radiuses, I guess it's okay too, as long as you don't have anybody who speaks Latin well. The diameter really is a very special example of something called a chord. C-H-O-R-D, chord, like a musical chord. And a chord is a line segment whose endpoints are on the circle. And therefore we can define a diameter as a chord that contains the center of the circle. So the chord is a general line segment, endpoints on the circle. The diameter is a special chord whose length passes through the center of the circle. How many chords can you draw on a circle? Well, infinite number. I mean, there's chords all over the place. And you'll notice as the chords get closer and closer to the actual circle, they get smaller and smaller. And then we have what's called an arc. An arc is a piece of a circle. Just as a line segment is a piece of a line, an arc is a piece of a circle. It has endpoints. And in fact, those endpoints can be the endpoints of a chord. Some people would say that an arc is simply a piece of a circle cut off by a chord. Now, for many, many generations back in ancient times, people were concerned with the relationship between the diameter of a circle, we know what that is, and its perimeter. And the perimeter of a circle, the distance around, was given a very special name. It was called the circumference. It's very interesting. I used to live in Atlanta. In Atlanta, there's a loop highway, I-285, that is called the perimeter. But on some road maps that I've seen, some official maps, it's called the circumferential highway, which means it was someone who was a fancy math major who understood that perimeter of a circle is a circumference. And the ancients were concerned of the relationship between the circumference and the diameter. It's even mentioned in the Old Testament, by the way, the original translation was that the circumference was 3 times the diameter. There have been recently some scholars who've indicated perhaps those folks had a better idea than that. Anyway, we know it's more than 3. And finally, in ancient Egypt, where people wrote in Greek because they were influenced by the Greek, this was after, I believe, Alexander the Great had conquered Egypt. But don't quote me, this is not a history tape, it's just what I'm telling you what I've read or heard. The people defined the ratio between the circumference and the diameter as pi. Not apple pie or cherry pie, but the Greek letter pi, sometimes spelled P-I in English. And the Greek letter pi looks like 2 T's that have been sort of joined. And the reason why they use that is because that is the Greek letter that makes the sound that P makes in our alphabet. And they were looking for a proportion. And we talked about proportions. Proportions are equal ratios. What they said is the ratio of the circumference to the diameter of one circle was equal to that ratio of any other circle. The ratios were in proportion. And therefore, the Greek word for proportion, which started with the Greek letter pi, was this ratio, approximately 3.14. At many universities, you may have computers that kick out the digits, and they're into the millions of digits for pi, because pi is an irrational number, something we talked about with square roots. Pi cannot be written as the ratio of 2 integers. It is not a repeating decimal. It goes on forever and ever with no cycles. 3.14159 is as far as I've memorized. I'm sure some of you could sit down and memorize 20 or 30 places. Sometimes we use 22/7. You may recall that 1/7, the first 2 digits in the 1/7 cycle, is 1/4. So 22/7, 3 and 1/7 would be 3.14 if stopped at the 100th place. Again, when we're measuring the circumference of a circle given its diameter, we are only concerned with an approximate measurement, because pi being an irrational number, we cannot write precisely. But again, unless you're a paramecium, rounding off to the 100th place or even the 1,000th place is probably good enough. The formula for the circumference of a circle is pi times d. Pi being this ratio, approximately 3.14, d being the diameter. Okay. Oh, you say, wait a second now, there's another formula up there. Well, of course there is, because we said that the diameter is twice the radius. And therefore, we can substitute 2 times the radius for the diameter, and we have 2 times pi times r. Earlier, in an earlier lesson, I mentioned that algebraically, when we have symbols that are letters, like pi and r, we don't have to put a multiplication symbol. So we could write also, if we wanted to, the circumference of a circle being equal to 2 pi r. 2 times pi times the radius of the circle. I believe it was Archimedes, an ancient mathematician who lived in the Greek world, who discovered the area of a circle in terms of pi. And what he discovered is pi times r, or pi r squared, will give you the area of a circle. Now, notice that we've multiplied the radius, which is a distance measurement, times the radius, which is a distance measurement. And that's important because, as I said earlier, every time we compute the area of a 2-dimensional figure, we will always multiply a distance measurement by a distance measurement, and both distance measurements have to be in the same units. So r times r, again, the area of a circle will again be in square inches, square feet, square meters, square centimeters, whatever it might happen to be. We've talked about a circle, we've talked about the triangle, and we've talked about perimeter. Let's talk about three-dimensional figures. On your screen you see a graphic that shows us 5 very common types of three-dimensional figures: the cube, the prism, the cylinder, the pyramid, and the cone. The cube, as we already have seen, is the basic shape in three-dimensional measurement. When we're measuring volume, it's always measured in cubic inches or cubic miles, what have you. A cube, you'll notice, is a three-dimensional square, some people say. A cube has 6 faces. All of the faces are squares. Okay, and therefore the edges or the sides of the cube are all the same measurement. A prism has 2 bases. The prism in your picture has triangular bases, a top and a bottom, or a left and a right, depending on how you're orienting the prism. All the other faces of the prism are rectangles. So in the triangular prism, there would be 2 triangles, a top and a bottom, the bases, and then 3 faces or sides that would be rectangles, connecting the 2 bases. You could have a square-based prism, or a rectangular-based prism, which is what we called a rectangular solid, or a box. You could have a prism with 5 sides, or 6 sides, or as many sides as you wanted. All of those sides would be rectangles. What would happen if the bases of a prism were circles? Well, then you'd have a cylinder. And you say, wait a second now, I don't see any rectangles in that cylinder. Because we said that all of the other faces of a prism would be rectangles. Well, take that cylinder. Imagine you used up a roll of paper towels and you had just the cardboard roll inside. That's a cylinder. Take a scissors and actually cut a straight cut through from the bottom to the top of that cylindrical shape. Open it up. What do you have? You have a rectangle. So indeed, the face, the side of the cylinder is a rectangle. Then we have another basic shape called a pyramid. Of course, the pyramids of Egypt are very famous. A pyramid simply has a base and a vertex, a tip, a point at the top, and has triangular sides. The pyramid could have a triangular base, a square base, or any type of polygon base, but all of the sides, of the faces of that pyramid going up to the vertex would be triangles. What if the base was a circle? What if the base was a circle? Well, then you have what's called a cone. And in fact, again, you could say, I don't see any triangles in that cone. If you take a cone and slice it the way you slice that cylinder and open it up, you would see a triangle. In fact, that's how you'd make a cone. Take a piece of paper, cut a triangle out, turn it, roll it around, and you'd have a cone. So these are the very basic shapes. We're not going to go into great depth into three-dimensional shapes. In fact, the 2 lessons we've done on geometry just barely scratch the surface of geometry. If you are personally interested in learning more about geometry, of course, there is an entire series by the teaching company on geometry. You can certainly purchase that and then just get filled up to the very top of your brain with information about geometry. What I'd like to do right now is to do a little arithmetic that involves geometry. We've learned about perimeter. We've learned about area. We know that the area of a rectangle is the length times the width, and that the perimeter of a rectangle is 2 times the length plus the width. That is the length plus the width, and then double it. So what we're going to do is a little puzzle here. We'll start off with a simple problem and allow the problems to get a bit more complex as we go along. We're going to have 4 columns. We're going to have length, width, perimeter, and area. I will fill in 2 of those numbers, and I want you to stop the tape each time I do that and compute the 2 missing numbers. Okay, let's see. The first one, we have a rectangle whose length is 5 and whose width is 8. I want you to stop the tape and find the area and the perimeter of that rectangle. Well, the area is typically the easier of the 2 to find. The area is length times width. 5 times 8 is 40. Now notice we haven't talked about units of measurement, but if the length and width were in meters, this would be 40 square meters. We'll just go ahead and talk about the numerical answers. The perimeter, well, we got to add the length and the width. 5 plus 8 is 13, and double that, we get 26. That was a fairly simple one. The next one is just a little bit more complex. Let me go ahead and erase that. Because this time what I'm going to do is I'm going to give you the length, which is 6, and I'm going to give you the area, which is 96. And you've got to find the width and the perimeter. Do that now, please. Well, let's see. We know that the area is the length times the width. So we really have is a missing multiplier problem. 6 times what is 96? That is 96 divided by 6, I believe, is 16. So the width must be 16. Well, now, length plus width is the semi-perimeter. That's 22. And double that, we get the perimeter. Double 22 is 44. So you'll notice we had to use some skill there to use the formulas we had. The length times width was area, and then use our knowledge of missing multiplier problems to solve for the width. Here's another one. In this case, let me give you the perimeter and the area. The perimeter is 24. The area is 20. Given the perimeter and the area, I'd like you to find the length and the width. Stop the tape, do the computations, and come back when you have them, please. Well, let's see now. This isn't quite as easy. And really what we have here is a puzzle. We'll talk more about solving puzzle kind of problems in our lesson later on problem solving. What we have is we know that the area is length times width. So the length times width is going to be 20. Well, we could be 1 times 20. But wait a second now. If the perimeter is 24, that means the semi-perimeter, the length plus the width, must be 12. Is 1 plus 20 equal to 12? Hardly. Well, we could use 2 times 10. Is 2 plus 10 12? Yes, it is. So it would appear that the length and the width are 2 and 10. Double checking that, 2 plus 10 is 12. 12 times 2, the perimeter is 24. And 2 times 10 is 20, the area is 20. So that's how that one works. That was not too bad, but again, it was not quite just using a formula. You had to use some problem-solving skills. Let's erase that and do one more. And this one I think you'll find a little bit interesting. The perimeter is 101 and the area is 25. And my students always say, you can't do that. The area has to be more than the perimeter. Yes, you can. Try it and see if you can find out the length and the width of this rectangle. Now we know that the length times the width has to equal 25. And I believe there are only 2 sets of whole numbers that'll work there. 1 times 25 equals 25, but 1 plus 25 is 26. 2 times 26 doesn't come close to 101. And of course 5 times 5 is 25, and 5 plus 5 is 10. 2 times 10 is 20. Notice also that this is an odd number. How can we add 2 numbers or multiply by 2 and get an odd number? We have to have a fraction. Aha! That's the hint. We need a fraction. So let's try a half. A half times what equals 25? Now, people will say it's a half of 25. No, it's not. A half times what? Obviously, multiplying by a half will make it smaller, so we need a number that's twice as big as 25. A half of 50 is 25. And notice that a half plus 50 is 50 and 1/2. And when I multiply that by 2 to get the perimeter, I get 101. So in this particular case, the length and the width are 50 and 1/2. The problem is made a little bit more difficult because if you weren't considering fractions, you thought there was no answer. Okay, what did we learn in Lesson 20? Well, we learned about perimeter. We learned that perimeter is the distance around the outside of a figure. We learned about triangles. We saw different types of triangles, and we saw that the area of a triangle is 1/2 times the base times the height. We learned about circles and the various parts of a circle, and we saw that the perimeter or circumference of a circle is pi, approximately 3.14, times the diameter, or 2 times pi times the radius, and that the area of a circle is pi times the radius, or pi r squared. We also looked at some three-dimensional shapes, just a brief look to introduce some very general types of three-dimensional shapes. And finally, we looked at some problems involving area and perimeter of rectangles. In Lesson 21, we'll learn about graphing in the coordinate plane. See you then.